Hello, YouTube. We're getting closer to crossing that off. I'll put the other X off when the engine is in the car. We're going to jump right back into the discussion on the build of the 489. We're going to run right over to Ken's shop, and he is in the middle of taking the bearing cap off so that we can put a bearing in the block and the cap back on and measure the vertical oil clearance between the crankshaft and the bearing. So here we go. So we're removing the cap to put the bearing in.
Yep, we're going to wipe off all the oil and honing residue just to make sure we don't get on the bearing. We'll pull the cap off, put it in, we'll torque it, and we'll go measure the crankshaft, see where we're at.
All right.
And then we'll see what the vertical oil clearance is. And then we can either tickle these smaller or bigger depending on which way we got to go. At this point we're talking tenths, so 1/10,000th of an inch, so 0.0001.
That's 10,000ths.
Yeah, 1/10,000th.
1/10,000th, yes.
Or 10 millionths of an inch. Just to put it into perspective. It's amazing that these hones can hold that tolerance. When you look at it, it's a segmented cylinder that you're honing.
Yep.
With nothing here to hold it, and then these are all individual stones and guides.
Right.
On one mandrel. Let's get this kind of cleaned up. Bearing back in. So you can see the cap. Those are just little scuff marks from us bringing the stone in and out, but basically I ground them all, brought the diameters in, rough bored them. I think these were 80,000 small, and then that's kind of where we're at. So tanks go together. You can see how that cap is lifted. See that gap? I'll let you get in there. That gap, because this cap it registers on these outside edges. So what happened when this got hot, the original cap sucked in and they would move back and forth. These new ones they'll draw right in, they'll repeat side to side.
Okay. What exactly is a bacon blast?
So basically they'll take this block, there's a furnace, either it could be gas or electric, like a kiln.
Okay.
Takes it up to 700 degrees.
Okay.
Pretty much all the grease and oil turns to ash at this point. Paint burns off and everything. And then what you do is, while it's still hot when it's done, like hot, you can't touch it. Just for an example, I picked up one earlier from them and I needed it right away. It melted my bed liner when we put it in there because it didn't have time to cool down. So usually what you do is, and the idea of leaving it hot is, as all the particulates in here, in the coolant jackets, sometimes a little stainless steel wire or some pellets, whatever metal they're using for tumbling and shot, will get in there. So when it's hot, there's no moisture, it won't stick.
Okay.
So I think that's pretty much the general purpose of why they do it. So you'll take it out, you'll put it in the tumbler or the shot blaster, shot blast it. It's basically two big paddles and probably 3 horsepower motors, throwing it against this as this rotates, and you can see it does a nice job. The problem is, any machine surface can be damage prone. So certain blocks I won't do, because there's certain surfaces I can't remachine.
Okay.
This, we planned on blueprinting it, so we knew we were going to line bore it. So what I did was I actually roughed it out, roughed the caps, clearance the block, and I'll go through that a little bit more, then sent it and had it bacon blasted. Deburred everything, just so it breaks all the edges. And then after that, we got it back. We're gonna do this line home, finish that. Then after that operation, I had a fixture, work off the center line of the crank, determine our deck height, which is the top of the block where the piston is. And then we'll machine that, we'll deck the block so it's parallel and square to each other. And usually we can hold it within a thou, end to end and side to side. So after that, then we're going to bore it out off the deck so it's 90 degrees and then finish home with the torque plates. So we're targeting, anywhere between 2 8/10 to 3 2/10, somewhere around there for vertical clearance. gives me like half a thousandths total tolerance. Hopefully we can get it pretty low. I mean, 3 would be optimum, but I'm gonna give myself a little either way.
Okay.
We're talking tenths. So.
Yeah.
These are 100 foot-pounds from the RP.
So you're not worrying about stretching bolts, you're just torquing them.
Well, it's hard to measure stretch on a main stuff.
Okay.
You know, we can't get to the other end, so I'll go off whatever the manufacturer's suggestion is. Connecting rods, they've gone to stretch, as you all know. They measure that point of where that rod bolt will retract back, so it's always under tension. I'm sure everybody measures them a little differently. Whatever works for you. I always kind of feel just a little bit of friction on is how I do it. You could measure each one of them if you wanted to and kind of split the difference. Usually these manufacturers are pretty good at grinding. I'm just feeling the resistance across the crank. You don't want.
Okay, you're not looking at the reading, you're just feeling resistance.
I'm kind of using like a no-go right now. I want to know that it kind of goes the same on both. I mean, if I'm measuring it, there's a stack up here with me measuring it with a micrometer like this. It could be off a couple tenths. This kind of allows me to look and kind of feel it. I know where it should be.
When I make spacers for like the 4 bars, that's how I do it. I make one too big, one too little, and then it's a no or no go.
Yeah, that's a good way to do it. So the micrometer, so ours is at 2 inch, 7, 48, and 5/10. I'm gonna replace the indicator. This is a pretty nice indicator. If you look, that's a tenths indicator. So that one is 1/1000th of an inch.
Okay.
And so is the one we use in the line bore. You try to use 1,000, so you can't go that small because you're just going to use up all the tolerance in the gauge. So basically right now I'm zeroing this.
Mm-hmm. And then you're going to compare it with a bearing.
Yeah, we're going to compare it and see where we're at. So this technically is what the crank measures. Now I'm going to come in here and see what our vertical oil clearance is. So right there, we're about 3 or 4 and a tenth. So we're a little big, so probably what we'll do is we'll cut these caps a little bit and bring that right down.
Okay.
Or what we can do is, so these are, I believe these are extra clearance bearings. So that crank's on the lower side. So the X here is extra clearance. Really, if we change the bearing, we go to a standard non-extra clearance, will be rated 3. This X is 1/1000th of an inch bigger, or smaller thickness. Because I'd rather not touch that. If that's it, we're already holding all these at 5/10.
Yep.
We know if we change that bearing to a standard one coated, that'll give us 3 on all of these.
All right, so we have to order new bearings.
I might have some here.
Oh, okay.
Give me 1 second. So I can show you this, Glenn. So this is a very expensive sun and bore gauge. Let's see how long it is. So this is also tenths. So if you look here, each one of those increments, as it shows you in there, with a 1/10,000th of an inch. So we're going to come through. Glenn and I earlier measured this so we could see where everything was. I thought we'd be close. So right there, if you look, we are at 5/10, just under the max on this. 5/10. 5/10. And I believe this one was right at 3. It's 0. So I usually run a little bit more on the thrust just because it's such a bigger bearing. Mm-hmm. You just feed a little bit extra to your thrust bearing.
Okay.
Let's see if you have a converter in your drag racing. So let me see if I have some other bearings. I'm glad we could save this block, you know.
Well, I didn't know that the block was in jeopardy.
Neither did I until I got into it. I was like, oh. I'm like, I think it'll clean. That's good. I'm like, Jim, I'm going to have you bacon blast it. I want to really get all the shit off of there. I'm like, I better do everything else. Okay, you ready?
Yes, sir.
Okay. This is a CH100. It's a Sun and Line home. It's a pretty manual operation. There's no CNC here. We basically have, let's say I got 5 different manuals or different diameters depending on different bore sizes. This is a 2.7, which we'll set up for this big block. We're gonna come in here, take our time. You can see that is a long home. It's segmented. What we're gonna do is this little knob down here controls how much tension is on these stones. We're gonna drive that stone into that bore. And then it's, whenever you do any kind of abrasive machining, I mean, most people have done some type of sanding, whether it was a dresser they were refinishing or maybe a fender on a car where you start out with your 40 grit and then your 80, 120, 320. Kind of the same idea here. My problem is I can't change this out when it dulls. So how this stays sharp is if you looked under a microscope, there's basically a composite material that's mixed in with the silicon carbide or whatever they make these out of. It could be aluminum oxides. And how it stays sharp is if you looked at it, they're all like little teeth. They're all jaggedy little pieces. And the harder you use them, they break off. So that breaking off allows them to stay sharp. If you've ever seen somebody dress a wheel on an old bench grinder, they used to have what they called a spur. It had these little wheels on an axle and you would put them in, and all it would do is, if you ever spun something on a brush or anything on an axle, you know how fast it goes. Well, that spur would dress the wheel. It would knock that off and open the wheel up so it was exposed and had more sharp teeth. I call them teeth. So they could machine away at whatever they're doing. These stones work the same way. So abrasives, the problem is as you're removing steel, it's also removing this. So you're always trying to control that size. So when you get something this long, how do you keep this from not tapering? So we have from this diameter to this diameter, we're able to maintain a diameter of no less than 1/10 between all of these, 1/10,000th of size of vertical clearance, which is crazy when you think about it. And then on the other side, you can see there's a shoe here. That shoe is a guide. There's no tension on that. That's done mechanical. So what we do is we put this in the bore. We put an indicator on here, and I indicate this in so it runs concentric to the bore. I'm not going to do it right now, but just so you know. And then depending on what you want to do, you can tailor how this cuts, because you can have this be prevailing or not prevailing. So what cuts first, the guide or this? And it oscillates, and you can make this round hole in an ellipse if you had to, or if it was tight on there, you wanted to do that. So there's a lot to this. I'm no expert on it. I've been doing it for 20 some years. I just kind of take my time and do it. We flip the block a lot so that your directional of your hone also changes. And sometimes,
excuse me.
no problem. Sometimes that allows you to open up the stone so it cuts a little better. We're always trying to maintain this stone so as it wears, it stays concentric and it also doesn't create any taper. So the more you can kind of move it around, you can do it. When we cut these caps, we want to maintain that diameter. So let's say this one is 3,000 small. I want all these 3,000 small vertical. If this one was 6 and this was 2, it's going to put a condition in my stone like a taper, because it's trying to compensate for that. So what we're going to do is we're going to kind of set this. We're going to take a couple light passes, and then we're going to measure it. It uses basically just honing oil. Mine's kind of clear. It's just a different brand. It's actually a grinding oil you can buy from Blazo Grind. I think it's C10 or something. I can't remember exactly the number.
I've seen red.
Yep, red, dark brown. Some guys make their own. So we can release this. Allows me to have no tension. If you watch, you can watch the stone come in and out. See it? So there's a spring in here. The spring is what keeps tension on all of these. They have a tapered shoe. So they're doing this and coming up on plane. So we're gonna back this down a little bit. Release, pull back. There you go. And then we can control that. This is just a coupling. So I usually open this up, get that in there, turn the oil on. There's stop set. I do it a little differently. I always try to bring my stone a little bit beyond whatever I'm cutting so that it never creates like a bell mouth on the end. Some guys don't do that. I don't know. Maybe there's some reasons not. So. Okay. So we're talking tenths of an inch here, not thousandths, but 1/10 thousandths of an inch. Try to pull it out even. In other words, the abrasive leaves little marks. Doesn't really change the size, it's just aesthetic. Okay, now we're going to measure. Let's see that. Temperature matters. You're talking 10 thousandths of an inch. I usually let them sit overnight. So right there we're at 5/10, just under the max tolerance. 5/10, 5/10, 5/10. Can you see that, Glenn, on there?
No, that's all right.
Okay. And then this one's always going to be a little bit bigger. That's where I cut it. We're rated 0 on that one. 0 and looks like about 2/10.
So have you weighed all the pistons at this point?
Yeah. So what I do is I actually work from an average.
Okay.
You can literally, so you can see that's actually from the manufacturer. That's 579 grams. This stuff today is not like it was 30 years ago where you would buy a forged piston. It could have 20, 30 grams difference. It was just crazy. And what we would do is we'd set them up in the mill and start milling with a key seat cutter underneath the boss. A lot of monkeying around. It's so nice today. Don't really get into that. Same with the rods. I mean, why shouldn't they be, right? The density of the material is not changing. It's pretty consistent.
Mm-hmm.
So if you can hold tense and everything, I don't think you're going to have an issue. So rod bearings. All these bearings that we are using are what they call H series. They're a performance bearing. I don't know if people realize that. And what I mean by performance, this bearing insert, this is narrow. So when you look at this box, and it says CB is connecting bearing 743HN. H is performance, and N is narrow.
Okay.
Why they make it narrow is because your aftermarket crank has a giant fillet radius in there to make it very strong. Years ago, what they did was they used to chamfer the bearing. So when you bought a bearing years ago,
It'd have
it
a
had a big chamfer in it.
Okay.
And then I think they realized it'd probably be easier just to make a narrow bearing. I don't even know if you can get them without narrow one anymore. Might be able to, I don't know. Makes it a lot easier. Like some engines, I have fixturing to chamfer bearings. Like on the Buicks and stuff I do, they don't offer an H series bearing, so you chamfer it to narrow it. But that's that, in case anybody's wondering. So these rings come with the Wiseco pistons. I'm not really certain who manufactures them. Sometimes you can tell. Sometimes there's a insignia on there from whoever the manufacturer is. Usually Total Seal will have a TS on it.
Yeah, this time you only found top on it.
Yeah. Maul will have an M on there.
Yeah.
So it's hard to say. A lot of the Wiseco stuff comes with Total Seal. So does Icon pistons. If you look at those are Total Seal rings. But it's a Molly ring. It's a what they call a barrel face. And if you look, it has a chamfer in here. It's very conventional, keeping this very simple. It's a 16th inch ring. The second is also the same thing. This is what they call a ductile iron ring. It's a little bit softer. It's used for scraping the oil. That's really what it does, is control the oil. This one has a moly surface. If you look here, you can actually see the difference between those. So if you ever don't know which one it is molybdenum surface. And I don't know exactly how they do it. I wish I did. It's been around a while. I have seen pistons rings that are manufactured that were in the wrong application, and that system all deglazed and came off of there. So it almost looks like it's machined and pocketed. And then it's a standard, this looks like a Hastings oil ring to me, which they might make them for everybody. All these manufacturers, I think it's probably the lowest bidder.
Yeah.
I'm not going to say that's not a bad thing. And then this is what they call a support rail. If you look, you can see it overlaps. So this is universal. This supports the ring package here. If you look, we push the wrist pin up into the oil passage. Whoops, well that's a good fit. We pushed it up into the oil ring. So to support that, this ring goes on first and acts like a shelf for it. So that oil ring is supported there. Almost all your stroker motors have something like that. Whether it's a 600 bore 383 with a 6-inch rod, usually going to do that rod. 5, it's not a huge long rod. This is a short deck. So this is a little bit more standard. What we did was we gained in the stroke, so it's a 4 1/4 stroke. So we had to make up for the difference in the piston, where that comes from. When we do the decking, we're going to measure all this. We'll do the math, and this will establish a deck height from center line to compression height of the piston. These are the used for retaining. Never used these before, you know they can be difficult. The installation's easy. The uninstallation is difficult sometimes. Makes your fingers pretty calloused after a while. So that's everything there. What we're going to do is we already measured all this stuff. So what I'm going to explain is when we go to the computer, you're going to see the numbers of what the stuff weighs. And we work from an average. So we went through all of them. We take an average of what the rod weight is. We use that. We're only chasing a gram or two. It's not a lot. And the same with the pistons. The manufacturer weighs them. They're all right there today. It's really nice, the rings. So we're going to go check that, and then I'll explain what we have. We have reciprocating mass, and we have rotational mass. I wish I understood a little bit better the science behind the programming of how they do it and what they're doing to establish this. But if you picture this going round and round, right, you can see that this is reciprocating, so the piston, the wrist pin, and supposedly the end of this rod reciprocates. And then the big end and the bearing rotate. So when you look at how the software is written, that's what they determine for that. And then we're going to basically, it uses a standard SAE RPM range in oil. So I don't come up with this. Some guys play with the RPM range. I keep everything pretty simple. We're going to go at 550 RPMs. We're going to rotate this assembly. We're going to work on 2 planes. And inside there basically is a sensor. It's kind of like a strain gauge or a load cell. It's picking up that vibration, and there's an encoder. So it knows out of 360 degrees exactly where that is, and then the software kind of does everything for us. I think years ago, I never really did it, but I've seen them do it. They actually would use a gauge, and it would be, I imagine it was some type of either electrical voltage change, and they could see it. I don't know how they did that. And then that would tailor to where it was radially.
Okay, well, I've seen it where they have a photo light going to a strobe light.
Yep, strobe light, just another way to trigger where you are. This has just a simple encoder. And I'll explain that. So that's kind of where we are. So we're going to go over the machine. I'll bring up the software. We can see what the bob weight was set at. And then how we make up the bob weights and then install them in the crank. Okay, what we have here is basically the crankshaft and the bob weights. We'll kind of walk through where the bob weights come from based on what we just talked about. Knowing position, it's like on a tire machine. You want to know where it is. This is basically an encoder in here. An encoder could be an optical encoder or a magnetic pulse, just like your crank trigger. This tells us out of 360 degrees where we're at. Inside these two heads, these are what they call planes. So everything is based on the front and rear main, and we're really going to try to just work in this area if we can, in this area. As you can see, there's some holes in here. Sometimes the manufacturer roughs it in. If you call Eagle or Scat or Callie's, they'll give you a recommended what this crankshaft was designed for a bob weight.
Okay.
And it'll give you a range. Perfect example is I have a Callie's crank that came in. I hadn't used one before, at least this model. And I called them because I wanted to verify. When I spun it, it was like 200 some grams I had to remove. I thought it was kind of excessive. And I called them and I gave them the bob weights and they said, Ken, that's pretty much about right. Our calculation's like 190. So I said, I'm in the ballpark. I just wanted to verify before I go and remove any material from a crankshaft. You can add material. There's a couple ways to do it.
We had to do that with the dragster.
Yeah, the Pontiac. It's a little bit of work. I'm not going to get into that. That's a whole nother thing. These are nice. As you can see, we're just removing weight. So what we're going to do is we're going to spin this, make sure everything's clear. It can get nasty if it wasn't. So now if you watch up here, you're going to see it does a safety check. It's saying, hey, it's in the range. That's actually the tachometer by 100, so at 550, boom, it starts acquiring data. So if you put your hand on here, you can feel a slight vibration. And it's identifying where it is. It's going to acquire the data. And then it's going to show you both planes. We have the left and right plane up there, those circles. Boom. So right now we're at 3.8 grams on the back. That's pretty much in tolerance. If you could see, it's telling you you have to go 39 thousandths deeper at 181 degrees. So if you look, I can put this at 181. Close right there. 180. You can see it's in red. It's telling you right there. There's not much I can do in here. I wouldn't do anything, but we're already the spec. So what we're going to do is we're going to finish the front side. It's got 14 grams. You're going to see this shift a little bit. I already balanced this, to be honest. I only left a little in here so Glenn and I could walk through the process. So we're going to go to the front. You're going to see this highlight up here. Should turn bluish green when we're on. There it is. So at 218, it wants us to remove a little bit of material. So you can see I already removed some here. What you can do is, and some manufacturers don't suggest it, you can go to this counterweight. If you wanted to pop a hole there, they're saying 140 thousandths deep. The problem is that drill is a 1 inch, so we can't do that. So what we're probably going to do is, I would probably go back to this hole here, and I'm probably going to remove a little bit more material and we'll spin it again. We'll see if we can negotiate where that is. I'd rather not drill more holes if I don't need to, if I can get it close. As long as we're within 3-4 grams, I think we're okay. I'm not going to chase it. If you want to see what 3-4 grams looks like, it's 2.5 grams. So you're just over a 5/16 washer. So it's not much. This has a tolerance to it. You can set it in here. We can chase it all you want. It's like balancing a tire. It's only so good. You're always going to have some vibration there. We have to have some tolerance. So what we're going to do is we're going to change the drill. We'll take a little out of this. So we'll pause a little bit and then I'll explain where the bob weights come from in the software. Glenn's 496 big block Chevy gasser. Rod weight, that's a total weight, 821 or 828.1 grams. The big end of the rod. So the big end, let me go grab a rod. The big end of the rod is basically if we're gonna measure this over here. This fixture goes in, you go on here, and then you measure this. You measure the total weight of the rod, and then you're going to measure the big end, and then mathematically they're going to separate that. There's an equation in the software that basically subtract it. They know the big end goes to the rotating, the small end then the difference will go to the reciprocating. Then you can see we got rod bearing here, 48.5, the piston, 580.5. These are average, so what I do is I do an average. If it's like 1 or 2 grams, I average them together, and I think that's fine. I'm sure someone will argue that it's not, but I kind of tell everybody this is like Dixie Cup. It's not Winston Cup. I mean, I can only do so much. It's not $1 million operation. So piston pin weight, that's our wrist pin. The pin locks, those little spiral locks we were looking at, there's 4 per on these, just so you know, there's 2 on each side. Piston ring weight, that's the combined ring, and then the support rail I showed you, that supports the oil ring. And then industry standard, they use 5 grams. So this is where I say that's an accumulation. They say, well, we have to put some oil on there because there's always windage. So I can't tell you exactly where this comes. When I buy this from the manufacturer, they make suggestions. You can play with the RPMs. I can play with percentages, rotating percentages. I don't really do any of that. I'm sure some of these race teams probably have more experience. I think as they go up on higher RPMs, I think they probably play with that. Maybe they see the dynamics there of noise. So we came into the industry standard. I don't know exactly how they came up with the 5 grams and how it gets divided over it. I'm sure that fluctuates depending on the stroke, the oil pan, and what you have. That oil gets thrown around pretty good. So that's what happens. All that information gets put in here. It basically spits out. If you look down here, is my bob weight, 2320.5. So this is a bob weight assembly. This is the same as 2,320 grams, 0.5. So you make all these up, and then they're incrementally split 90 degrees, as you can see, and then another 90, and then this 90. Position matters. If you play with it, you got to be careful. This distance from the plane, there's measurements that I put in here, and this is how it calculates things. So you can influence that. So some guys have gauges they put in here to make sure everything's equal. I don't know what the tolerance is. Maybe sometime when I have time, I'll see what a 60 thou shift influences it. It'd be nice to know. So that's kind of where we're at for reference. So what we're going to do next is we're going to change this drill out. We're going to go in this existing hole. I think what we're going to do is we're going to take a little bit out of that, kind of see where this ends up. The back, we're pretty good there. So we're going to go here, and then after that, if everything looks good, these holes would all get chamfered. This crank will get cleaned, wire brush run through everything, and then it'll get micro polished with what I call a cork bonded belt. I know it looks very abrasive, but it's actually cork. And it's I forgot what the grit is. It might tell us on the back. So that's on something
pretty fine.
Yeah, I mean on a crank like this, this crank is nitrided, so
You don't want to take much off.
you're not going to be able to take much off. It's probably, I don't know, it's got to be in the 60C for hardness. So this really will bring out the luster. We rotate it backwards so that you're actually always creating a burr away from the rotation. Everything has a burr on it. Just how close do you want to go? I don't know what the RA is on this. It's a ground finish, so it should be like probably a 20. So we'll get done, we'll polish it, wash it, and then that'll be ready for assembly. All these will get deburred. We'll make sure there's no sharp edges. So I think right now we'll change this out, and then we'll get back and we'll show you. We're going to take a little material out of this and kind of see where we can get it down to the tolerance. Okay, Glenn, we walked this over. We already had an existing hole there. They want us to take a little bit more off this side, but what we're going to do is we're going to take a little off of here, and maybe we'll set this, we'll go to 60 thou, we'll spin it, we'll kind of see where we're at, and then we'll see where the weight moves. So that's kind of what we're going to do next. Usually I put paper towel in here just to catch the chips. It's going to want to jump around a little bit. We're going to set this around there. Don't laugh. Just a little lever.
I see that.
I'm not really doing much, but it just helps. I'm going to stop short because I don't want to add material. I want to see if we can just take it out. Lock this. This crank is internally balanced. I'll explain what that means if not everybody knows. Originally, Glenn's engine was what they call an externally balanced, where the manufacturer designs the crank assembly so that there's not enough counterweight here, so they put a weight out here on the other side of this bearing, this plane. Let's call this a plane. So when you look at your balancer, and Glenn's going to show you a picture of his original one, it has a counterweight bolted into it. And the flywheel also does the same thing. There's another weight opposing to add out here on the other side of this bearing.
Same thing for a flex plate.
Yep. I'm not going to say it's right or wrong, it's just what they do. Usually when I do a race motor or something, we try to go to the internal. They say it's better just because now you're not trying to put a counterweight on either side of this main bearing.
Right.
I don't think it hurts.
So why don't the manufacturers do that right from the beginning?
Well, you gotta remember, it's a manufacturer, so it's an OEM by design. Maybe when they draw up these counterweights, I don't know how they actually do it. I imagine they draw the crank, they figure out the whole assembly, and then they'll go in and probably figure this out. If you use like SolidWorks, you can figure out the mass in here and where it is heavy in a 3D model. So I'm sure that's what they do, and probably they want to standardize this. Maybe it's forging, castings, whatever's going on there. So they might move that weight out here. Most of your LSs, your heavies, those are all internally balanced today. So I don't think you see it as much as you used to. Years ago, Pontiacs were internal on this end and external on this end. I don't remember how many grams it is, not a lot, not like this. Buick is external, like a big block Buick, both ends. Fords, 460s come either way, depending on what crank. Usually they're cast cranks, and I don't know if it helps them with manufacturing. They would usually do that. They would be external. Small block Chevys, really the only external small block Chevy was a 400. I don't know when they added the stroke, if they realized they couldn't put any more counterweight here, so they just added that weight out there. So, okay, we're going to spin this up. I think we're all out of there. Let's see where we're at. Spin. Sometimes I get a bump start, but she seems to be good. Now, if you watch this, you're going to see this reach its tap, 550 RPMs we talked about earlier, and it's going to start acquiring data. Boom, right there. And now it's basically looking at this pickup, and however the software is written, it's saying, yep, here we are, I feel this mass. And I don't know how they calibrate what that mass is. Okay, and we're going to be, okay, so we're 11 grams. We just took a little out. We wanted to see where we are. We were 14. It's still telling me it wants it up here. I think I'm going to take a little bit more out of here and see if I can just shift this before we go and poke another hole in here. Something to think about is the deeper you go with a hole, the less it responds to this.
Right, because the weight's not so far out.
Exactly. You know, it's like slinging a rock on a rope.
Right.
So you try to remember that. The other thing is don't put these holes too close together because they're targeting down a radius of intercept, and you could ruin a nice crank that way. Don't laugh about the bar. So I have a hard stop set here. I'm going to go right to that. Try not to punch any more holes in here if we don't have to. But I think we're going to probably have to. Feels nice, smooth vibration. Okay, 7.5 from 11, so we'll be going the right direction. Let's see where we are now. See, so we're moving that heavy spot away. So we could probably take a little bit more out of here. All we're gonna do is kind of, it's gonna diminish and get smaller, but eventually we're gonna have to take something out over here. Trust me, I don't wanna do any more holes than I have to. So at this point, you know, it's based on experience. I'm not gonna tell you I have 30 years experience at doing this. I might go and just take a little bit more out of it just to see. And then, as you can see, it helps me because it gives me this hole shifted over a little bit. And you can see it's not gonna be much. It's 77 thousandths. So
Right.
that's, you know, a spark plug gap. So either we could come over and just spot that, or we could try, I don't know, kind of 6 to 1, half does the other. Another 40 thousandths. Don't forget, as we get deeper, it does less also.
Right.
Alright, I like it. Let's see if we influenced it. I'm going to spin this again. Okay, from diminishing returns, we're probably not going to get any more out of it at that hole. We'll see. We're really close. We're getting down there.
It's getting heavy.
Yeah, so we worked out of this hole, but as you can see, as we remove this mass, this gets lighter, and the heavy part goes this way. So if you look up there at 184 degrees, right there is where they want us to remove materials. We're up here somewhere, and it's only 51 thousandths. So we're gonna come up here, we'll center this drill. I'm gonna take and knock some of that carbon off of there from the nitriding, make it a little softer, and then we'll spot that out, and I think we'll be good. Okay, so earlier we talked about these cranks are nitrided. Sometimes you can kind of see the heat treat in them. I'm not like the heat treat expert. Nitriding, they basically hang them in an atmosphere. I think they draw a vacuum down, introduce nitrogen into it, and then whatever the curve is for heat treat. I know the place in Rochester, a Lindbergh heat treat, used to do GM cranks years ago. I don't know if they still do it. So we're just going to take a little of this off of here. Just helps my drill start a little bit. I'm not going to go with a smaller drill. If you do a smaller drill, what it tends to do is when you go in with a bigger drill, it'll chatter hard since it's only 2 flute. Maybe there's a trick to it. I don't know. This is just what I've been doing. I'm just going to check this. Let's make sure we're in center. If you ever want to check center, what you can do is you can put your ruler on here. It'll come down. Touch off. So if that was crooked like this,
Okay.
I can show you. Yep. Come like this. See that? Mm-hmm. So what I'll do is I'll just come in here, center it. I kind of know where my spot is. A little bit more.
A little more.
A little more. Thank you. Almost back to my 0. A little bit more.
Mm-hmm.
It's an easy way to find center.
That's neat.
You can do that on a lathe too. The timer showed me that. I'm no expert, trust me. So you can see it's kind of tough to drill these on a radius. It's going to want to push and pull, so we're going to have to play with it a little bit. We'll see where we are. Let's see how it cuts. But we're only talking 51 thousandths, right? So that's like a spark plug gap.
2 spark plug gaps.
Yeah, depending on if it's a race car. Check, that looks good. Let's see how bad she jumps around. So she's gonna wiggle a little bit on us, but once she gets in there, we'll be okay. Like I said, we're not taking much off it. So the software allows you to compensate for drill points too. So you can put in the drill point, the included angle.
26 or 37?
Yep, 128, whatever the included angle is. So they did their homework, did a nice job. Stop there and check it, maybe a little bit more. Okay. Some simple features that I thought was kind of neat. So not all the cranks, if you see the teardrop here.
Are beveled like that?
Yeah. You don't really want, we used to put a big chamfer in there and blend it, and then they found really by pocketing this based on the rotation that worked better because it would hold the oil in the pocket. Again, it's kind of like that
The other round main bearing.
around when you have a same idea how all this kind of works. All right, let's see where we are. Almost there, Glenn. I think we're good. So we're at 0.67 grams. That's pretty small. The 4.2, I'm not going to chase that end. I think we're good.
All right.
So I think that concludes our balancing of a 4 1/4 stroke internal crankshaft from Scat.
Outstanding.
I'd recommend this crank to anybody.
Hope you found the visit to Ken's shop informative. He certainly has a lot of information to pass on. The next time we're there, I think what we're doing is decking the block and boring the cylinders. Until then, if you enjoyed this video, there will be more.